Yes, good evening, learners.
Good evening, sir.
Yeah, so my skin is visible to you.
Sir, it is green in color, sir.
Sorry.
It is in green color, sir. I'm seeing a green screen.
Okay, just a minute.
Yes, sir.
Now are you able to see the screen?
So only green screen is visible, sir. Maybe I am having a network issue. One second, sir.
Because I have already said it.
Yes,
You
sir. Yes,
now it's
yes,
okay.
sir.
Yeah, okay.
Sir, let me see. I just joined in another way, sir.
Yeah, please.
Let us just go out.
Yes, yeah. Please try one another way. And Sanjay, so who's
Yes, yes,
yeah?
sir.
Okay, okay. Vijay Lakshmi, are you able to hear me? Vijay Lakshmi.
Yes, sir. Yes, sir.
So are you able to see the screen? Means this
Yes,
introduction.
yes. Introduction to polymer
Ha,
science.
okay.
I can clearly see the screen, sir.
Okay, 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 then it's okay. So we will wait for 2 minutes, then we'll start, okay?
Okay,
Let us
okay.
join, yeah.
Sir, actually,
Sir,
I have a
in my
doubt.
laptop it is not visible, sir. Now in
Huh.
phone it is visible, sir.
Okay, okay, okay.
Thank you.
Uh,
Yes,
excuse me, sir.
yes, yes.
Sir, actually, I have a doubt.
Huh.
Regarding the assignment one, you have given some solutions, no, sir?
Huh.
Actually, in that question number 10, 11, 12, it's
Huh.
regarding weight average molecular weight, number average molecular weight, and the other one is PDA.
Okay.
So here, actually, in your solution also, you have given the same thing.
Huh.
Uh, Here, the summation of XI it
Yes.
should be 10,800.
Okay. So I have corrected means when I was taking class, so
Yes,
I have corrected somewhere. I am not able to remember, but there are some mistakes, so I corrected that.
sir.
But still, if you have problem, then I will see. I will see and I will revert you
Okay,
next week. Okay.
actually, for
Ten.
each question we have two credits, no, sir.
Haha.
So this is the linked questions.
Okay.
So we have missed 6 credits because of that.
So you are saying that answer is wrong, like that?
Yes, yes, sir. Yes, sir.
Let me
So
check.
the method of solving it same, sir.
Ha
Uh,
ha.
if possible, I'll share my screen.
Yes, because see, to now I am going to take class for this week. So
Yes,
you
yes.
please let me note down and
Okay, okay.
it is week one, na?
Yes, yes, sir.
Week one, question number 10, 11, and 12.
11 and 12, sir.
10, 11, and 12. Okay,
Okay.
I will check it and I will actually this course is already means it is a recurring course. Okay,
Yes,
so
yes, sir. Yes.
so that's why if there is some mistake, then we have to contact with tutor means professor. So that's why because I am only what say I am only TA of this course for this
Okay, okay.
semester. So actually it is already old thing, so we have to if if there is some mistake, then I will contact to professor and make it clear.
Okay, sir. Okay. Thank you so
Yeah,
much, sir.
yeah,
Actually, I didn't know whom to contact.
yeah,
That's why I asked here, sir.
yeah. And I also saying I'm also sharing my email ID. You can write what is the problem actually.
Okay, okay, sir.
Sir, I also do have an issue in
Okay, sir.
last
Thank
week
you.
assignment. Sir.
Just a minute. Yeah, okay, so I have
Yes,
shared this email ID. You please write me. I will see the issue. Okay. Yes.
Okay, sir.
yes, sir.
Thank you so
Yes,
much,
sir.
sir.
Yeah, yes, Sanjay.
Yes, sir. I also do have an third week assignment issue, sir.
Third week. Okay, third week.
Yes, sir. Yes,
Yes.
sir.
So
Yes, sir.
third week question number.
Sir, seventh one, sir.
Uh,
I have mentioned the answer as 25.003, but
okay.
the accepted answer is 25. but in the question you haven't as mentioned the specific thing. I mean, what round of values?
Okay. So actually, I am not aware about that. You please write
Yes,
me.
sir.
You please write me this query. I will contact. Okay.
Yes, sir. Thank you. Thank you, sir.
So I think you have received my email ID from the mailbox.
Yes, sir. I got it, sir.
Okay. 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 So today we will discuss about assignment of week 3, and then we will discuss some important concept of ongoing semester, which is ongoing week, which is week 4. Okay. So I think we should wait because only 4 students are there. So we should wait for 2 minutes, and then we will start. Okay, at 6:05 we will start. If you are not able to hear my voice or you are not able to see the screen, please tell me. Okay, and also if you have some doubt, you can ask. Okay, yes. Okay, we should start now. It is a week 3 assignment. Okay, so question number 1. Consider a radical polymerization. Okay, uh, radical polymerization reaction was initiated by the following species separately. Okay, so there are two examples are given here, A and B. Okay, and what question is asking that there are the example of respectively. Okay, so we need to find out that which type of radical polymerization is there. Okay, so we discussed about three type of polymerization: thermal initiation, photochemical initiation, and redox initiation. Okay, so on the basis of that, if you remember, then you can answer it. It is very easy question actually. Okay, so Fe plus 2 and Fe plus 3. Okay, so this equilibrium I think you know very well. Ferrous and ferric. Okay, if ferrous will lose one electron, just a minute, just a minute, what happened? Okay, so when ferrous lose one electron, it will convert in ferric, and when ferric gaining one electron, it will convert in ferrous. Okay, So it is ferrous, OUS, and it is ferric. Okay. So what is that? Means it is a redox reaction. Why it is redox reaction? Because this iron, ferrous and ferric are species of iron. Okay, so it can take electron and it can release electron. Okay, reversibly. So that's why it is a redox reaction. Because if you see from here to here, so it is oxidation, and from here to here it is reduction. Okay, so it is oxidation and this is the reduction. So that's why in this reaction, if you this reaction I already explained, if you see it will because it is peroxide. Okay, so when it will be dissociate, it will make one radical like that. Okay, two radical, actually this type of two radical will be formed. Okay, and this extra electron, okay, just a minute. Okay, and the electron will be shared by the iron species, which is ferrous. Okay, so it is obviously it is a redox initiation. Okay, so this one is redox initiation. First is clear. Then second is already given here. See, it is very simple. This symbol is representing heat. Okay, if you are providing additional heat to any reaction, then you need to apply. You need to add this symbol. Okay, so it is nitrogen will be released when you hit this compound. Okay, nitrogen will be released and it will make this type of radical. Okay, this type of radical will be formed if this reaction will be proceed. Okay, so I think its answer is clear now. Okay, so first is redox initiation and second is thermal initiation. Okay, so answer C is correct. Okay, so question number 1, answer is C. Then question number 2, on increasing the temperature of three different type of radical polymerization. Okay, what we are doing, uh, temperature increase. Okay, if let me somebody in waiting room. Okay, so on increasing temperature, three type of radical polymerization, the molecular weight of produced polymer in reaction decrease. Okay, in first case, okay, so this is the common thing, we are increasing temperature, but the molecular weight the molecular weight is decreasing in first case, in second case it is increasing, and in third case it is remain same. Okay, so we need to find out the possible initiation mechanism. Okay, uh, I request you all please join on time. Okay, so I need not to let you in again and again. Okay, please join on time. It is 6, I will wait till 6:05. Okay, so you can join up to 6:05, then try to join on the miss this time duration only, otherwise it is very difficult to again and again. Okay, so what we are discussing here. Yes, we are here now. Okay, so in three cases you are increasing temperature. Okay, and the reaction rate, the molecular weight of product polymer is decreasing, increasing, and constant. Okay, so you can find out this by equation which we will discussed. Okay, but in general by common sense also you can answer this question, okay, because you are increasing temperature, okay, so reaction rate will be fast, rate will be increase, okay, so that what will happen, reaction rate will be increase, propagation rate will be also increase, and termination rate will also increase. So molecule will be formed, but its molecular weight will be decreased on when radical is initiated by thermal and thermal way, and if you increase temperature further. Second, okay, so molecular, so rate increase, but it will produce low molecular weight polymer. Okay, in the but in the photochemical way, in photochemical way it will be increase, okay, is with temperature increase photochemical, because reaction rate will be increase, okay, here initiation rate will be not affected because it is photo initiated, okay, so radical are generated due to photo initiation, okay, so it will remain same, but the propagation rate will be increase, okay, due to temperature increase, and so finally molecular rate will be increased. But in redox reaction, the redox reaction, because it is due to electron transfer, radical formed by electron transfer, then it will propagate reaction, so it will almost remain constant, okay, so A is right answer of this question. Now we will discuss on the basis of equation. So this is the equation, okay, detailed solution is this, and this is overall activation energy, okay, so if you put this value in this equation, you will able to find that it will increase, decrease, or whatever, because for thermally initiated reaction EXN has value minus 60, okay, so EXN value is negative for thermal initiation, okay, so here this value will be negative, okay, and negative negative it will be positive because it is negative, already negative is there, and this value is also negative. Then a pure photochemical, it is the value is around 20, so it is positive value, okay, and for redox reaction it is close to 0, okay, so in redox reaction it is 0, so it will not affected, but according to this value, negative value of thermal ionization, the it will decrease, the molecular weight will be decreased, but in just a minute, and in the photochemical polymerization, the polymerization rate will be increased. Just a minute. Okay, now we are discussing about the question number 3. So question number 3 is, styrene was polymerized by heating to 100 degree centigrade. Okay, self-initiated. Okay, it is self-initiated reaction. Okay, when you heat it at 100 degree centigrade, it will be self-initiated. Mean it will be self-initiated polymerization. Okay, then styrene was taken from three different sources. Okay, styrenes are taking monomer of styrene is taking from three different sources. Okay, so styrene monomers are taking from three different sources. Sorry. So styrenes were taken from three different sources, two of which might contain impurities. Okay, so if we are taking one, two, and three sources out of this, so one is pure, but these two other sources of styrene containing impurities. Okay, so now what? Uh, uh, so we did polymerization by taking these three monomer from different sources and then plotted percentage conversion with time. Okay, so for all these three sources we plotted this curve. Okay, we have three curves, we have data about, and we need to find out that why these curves are different. Okay, so this question already saying that in source 2 and 3 impurities are there. Okay, so that's why its conversion is low. Okay, percentage conversion if you see here y-axis. So first, which is pure styrene, it is conversion is very high with respect of time, but 2 and 3 has lower conversion rate. Okay, but what question asking again? So curve 2 and 3 were generated from styrene from the second and third styrene from second and third sources respectively. What is the nature of impurities? Okay, so what question is asking? Nature of impurities. Okay, by seeing this data or by seeing this curve, we need to find out that monomer are there. Obviously, then only polymerization is there. But which type of impurity is there? So that's why the shape of curve is vary. Okay. Okay, so see here means conversion rate is means it is for pure. So the conversion rate is constantly increasing like that. Conversion is constantly increasing, then it is giving distance, but it is lower than pure. Okay, but it is saying the same nature like pure monomer, but it is conversion is low. Okay, otherwise nature is same. So that's we can say that there is something which is decreasing the rate of polymerization. Okay, there is something which is decreasing the rate of polymerization. Okay, so it is called as retarder. Okay, so it is called as retarder. Retarder means the substance which decreasing the rate of polymerization. Okay, so it means it is like it is something you are going in one direction. Suppose you are going in one direction, okay, without air pressure, so you can move easily. But if you are moving there and some air is blowing like that in opposite direction, okay, so you will feel some type of resistance. Okay, same thing. So if retarder is there in the reaction mixture, so it will work like this air which is flowing opposite to your moving direction. Okay, so that's why second is curve is for retarder, but the curve 3 is showing a sigmoid curve like that. Okay, so why it is so? So initially, see up to here, this time you can say reaction is conversion is almost negligible. Okay, then suddenly conversion is increased, and again it is showing the behavior which is similar to 2 and 3. Okay, but up to this time the conversion is very low, negligible. Okay, so why it is so? So something is there. So we can say here time is 0 and here time is 5 minutes. Okay, for understanding only. Okay, so here time is 5 minutes. So up to 5 minutes something is there in your reaction mixture which is stopping the conversion. Okay, something is there in your reaction which is not allowing polymerization. Okay, so we can say that it is inhibitor means something which is stopping the polymerization. Okay, so inhibitor, then you will see that the reaction is increased, but also the conversion is not increase up to pure monomer. Okay, so that's why we can say yeah, retard up to here we concluded that here some inhibitor is present. Okay, from 5 minutes, because up to 5 minutes the conversion rate is negligible, so we concluded that there is some inhibitor is there. After that also the conversion is increased, but it is not up to this level. Okay, pure solvent. Okay, or you can say up to second, which also contain retarder. Okay, so obviously there is retarder is also present. Okay, so by this curve you can say कि retarder is also present. Okay, so the second type of monomer, second source of monomer only contain a retarder, but the third type of monomer source contain both inhibitor and retarder. Okay, so answer D will be correct. Okay, clear? So let me see something. Yeah, so nobody in waiting room. ठीक. Okay. So I think you understood the answer of this question. Okay, question number three. So see here, uh, inhibitor. I have already explained, but I will just read it out, so it will be revised. Inhibitor only inhibit the reaction for a while. Okay, for a while, for a period of time. Okay, so after that, normal reaction should be there. Okay, after that, normal reaction should be there, but it is not there. After induction period of inhibitor, after that also the rate of reaction was not up to level, so we can say some retarder also slow down the reaction of beginning. Okay, so this is the work of retarder and inhibitor. Here one additional information is given that an accelerator is compounds that accelerate the reaction. Okay, so sometime we also add accelerators which actually increase the rate of reaction. Okay, it is not part of this question, but for your information only it is given here. Okay. Okay, so now we are moving question number four. It is numerical type. Okay, so the benzoyl peroxide initiate polymerization of a monomer follows the simplest kinetic scheme. Okay, so kinetic is simplest. So and what is asking with all rate constant and A being independent of conversion. For a polymerization system with okay initial concentration is given, then initial concentration of monomer is given, initial concentration of initiator is given, and limiting conversion P infinity, which is called as limiting conversion, is 30% to limiting conversion of 40. Okay, so we need to increase. I think this question is similar question of our last assignment. Okay, so what we need to do, we need to change conversion 30 to 40. Okay, so there is one uh, you can say one equation. Okay, which will be which by using this equation you can easily find out. Okay, so how much I0 should be increased. Okay, so we need to find out that we what is our objective. Our objective is to increase the concentration, so limiting conversion uh, 30% to 40%. So question is asking that how much initiator concentration should be increased. Initiator concentration. So this question is I think repeating. So this is the way by that you can, by using this equation you can find out. Okay, so ln 1 minus p infinity. Okay, so p infinity and I0, it is direct relationship. Okay, so it is proportional. Okay, so this ln 1 minus p infinity is proportional to I0. So you can from this equation you can write this equation. Okay, now you need to put the value. Okay, so at 0.04 we need to find out. Okay, and for ln 1 0.04 it is I03. Okay, and if you this conversion is already given 1.43. Okay, so if you just a minute, what is given here? initial I0 is given. Okay, I0 is given 10 raised to the minus 3. Okay, so I0 for what? I0 for when conversion is 30. Okay, when conversion is 30, I0 is given. So I0 will be, you can put here the value of I0, and then you will able to find out the value of I0 of I0 which required for P infinity of 40%. Okay, by putting this value only you can find out. Okay, then question number 5. Okay, so let me start. Question number 5 is representing this reaction mechanism. Okay, two polymerization reaction were hampered by the chain transfer following the aforementioned mechanism, where the rate constant are treated as. Okay, first of all, you just understand this equation, what is happening. It is uh, radical. Radical is propagating. Okay, so it is Kp propagating reaction. Okay, so this radical is propagating to make polymer. Okay, then you can say it is a transfer reaction. Okay, KTR means you can say this is what we can say. It is a transferring chain. Okay, so Mn react with T and it will be like that. So it can react further. It will produce one radical. Okay, similarly this now this radical again can make other chain. Okay, it can be initiator for another polymerization. Okay, and it will make a chain. Okay, so it will be like that. So this question is asking, okay, so this is the second polymerization. Okay, so first polymerization is there and transfer happened in second reaction, then another polymerization is started. Okay, so two polymerization are polymerization are represented here. So what question is asking, two polymerization reaction were hampered by the chain transfer. Okay, so it by this polymerization we can say one number and it is two number. So the first polymerization is hampered. Why? It is due to chain transfer. Okay, in this reaction chain transfer is there. Okay, following the aforementioned mechanism, after that this so equation number, you can say equation number 1, equation number 2 and equation number 3. Okay, so after that aforementioned mechanism where the rate constant are related is. Okay, now the rate constant Kp, Ktr and Ka relationship is given here. Okay, so on the basis of we need to find out, just a minute. Yes, actually, fourth week problem will not share. Okay, because we cannot solve this question of week 4 before your submission date. Okay, it is clearly instructed that we can solve previous week. If we will solve all the question, then what is means it will be not fair. Okay.
No, sir. What I'm asking is, for before every week there is a example question will be solved. No, sir.
No, example question means we need to find out the assignment of last semester. These questions are for your last week assignment. Am I right?
Yes, sir. Yes, sir. These we
So
have solved and we have got the
ha
answer.
ha.
That's why I'm
Yeah, yeah.
asking.
But if you have some doubt in this question, then we can only share. But we cannot. If you have any doubt, you can write me. Okay.
Yes, sir.
But we cannot share here. We cannot share
Yes.
publicly. Okay. If you have any
Yeah.
doubt, if you are not able to understand, then just write me. I will try to solve. Okay.
Yes, sir. Sure. Sir.
Okay.
Excuse me, sir.
Yes.
Sir, is this week three questions?
It
What
is.
you found?
Yes, yes. Week
But
three.
what we have solved and sent us different questions, sir.
You solve week three different questions.
Yes, yes.
Actually, these questions are from you can say last semester course. Okay,
Oh, okay,
so
okay.
yeah,
Not this one.
so these questions are given to us to solve
Okay.
and make you understand that how question should be solved like that. But if you have any problem, I have shared this email ID, na, so you can
Yes,
write
yes.
me. So I
Yeah.
will, if you have doubt in any question or you found some mistake,
Okay.
some human mistake is also there. So if you are able to find out, then just write me. Okay.
Okay. Okay.
Huh.
Okay, sir. Thank you.
Okay. So where we are, yes. So now see KP, here it is given in first clause, it is given KP is very higher than KT. Okay. So KTR, transfer reaction is very higher compared to KP, and K is comparable to, similar to KP. Okay. So what will happen in this case? You can understand simply. Okay, if you are not going mathematically, then you can understand simply, because KTR is very high. So what will happen? This reaction, this reaction will be started, and after that it will be transferred in this reaction. Why? Because KTR is very high compared to KP. So this reaction will, the conversion of this reaction will be very low compared to transfer. Okay, so means whatever radicals which produced for polymerization, which will be okay, that will be converted in transfer reaction. Okay, then K is equal to Kp. Now after that K is also equal to Kp, so the rate of polymerization will be same. So finally you can say that the radical which are made for polymerization of first polymerization, eventually they converted due to chain transfer reaction, and finally started second polymerization. Okay, so finally you can say that second polymerization will be increased. Okay, so that's why it will make some small polymers, small molecular weight polymers, or small chains polymer. Okay, so we can say it is known as telomerization. Okay, so it is clear. Then second clause is asking that Kp is very higher than Ktr. Okay, so now just opposite case. So what is happening here? From here to here, this reaction is occurring but very slow. In second case, it is very slow. In second case, okay, I am discussing about that. So in second case, it is very slow. Okay, so what will happen? The amount of polymerization first will be very high. Okay, compared to transfer, and here also Kp is very high compared to K. Okay, so although some molecules converted, some you can say radical converted due to chain transfer, but also the K is very slow compared to Kp. Okay, so this reaction product is very small. You can say the second polymerization will be very small. Okay, and first polymerization will be higher. So by understanding this clauses, you can say. Okay, so yeah, so you can say the first second in second case, it will be almost normal polymerization. Okay, almost normal polymerization, but some, it is transfer reaction is there na, it is the rate of transfer reaction is very low, but it is there. Okay, so some radical will be transferred. Okay, some radical will be uh, some radical take part in transfer reaction. So that's why the rate of reaction will be decrease. So rate, which rate of reaction? Kp. Okay, so Kp, or you can say polymerization of first type of polymerization will be decrease. Okay, little bit. Okay, so we can say it will affect retardation of this polymerization. Okay, so the polymerization rate will be decreased, but it is decreased very little, but it will be decreased. Okay, why it will be decreased? Due to some chain transfer reaction. Okay, due to some chain transfer reaction it will be decreased, but then it will be make polymerization because KTR is very slow. Okay, so some amount will be decreased. You can say if for example, if it is initially it was 100%. Okay, so we can say 10% chain transfer reaction is there. Okay, so now it is 90% only. Okay, so the polymerization of first molecule is now 90% only. Okay, so something is like that. I'm giving only example. Okay, for your understanding, it is nothing about an effect. Okay, so it is retarding or retardation of polymerization first. Okay, so finally we concluded these both clauses. Okay, and now I am going to answer. Okay, I have already told you that by the close one, we will able to produce telomerization, and by the closed second, we will it will be retardation of the polymerization fast. Okay, so answer C will be right. Okay, now question number 6. It is also numerical. Calculate the half lifetime. Okay, in unit of minutes of an initiator in toluene at 70 degrees centigrade, uh, given its dissociation rate constant kd. Okay, so we need to find out t half. Okay, and uh, in units of minutes. Okay, uh, it should be okay. Okay, let me check. And initiator, units of minute of initiator in toluene at 70 degree, and given its dissociation rate kd is given. Okay, so we know that so so it is radical polymerization which follow the first order reaction. Okay, so you can find out the reaction which is 0.693 and reaction rate. Okay, so kd is already given, dissociation is given. Okay, and what we are using, initiator in toluene. Okay, so in toluene we are using it as initiator. Then we need to find out dissociation rate is given, and we need to find out that what will be the half lifetime. Okay, so by using this formula, first of it is first order reaction, half time, sorry, half lifetime formula. So you need to use this same formula here, and by putting only value, you will able to find out. Okay, kd is already given, it is already constant, so just you need to divide this 0.693 by this kd value, which is 693.10 as a minus 3. See, it is very simple. So it is 6.93 into 10 to the minus 3. Okay, so you can write like that upon 6.93, or it is 693. Okay, because it will multiply by 3, and it is 6.93. Okay, so if you remove this to 0, it is 100 minute. Okay, so the answer will be 100 minutes. Okay, yeah, it is given here also. So by using this equation, I think you know about that it will follow first order reaction. Okay, so by putting the value in this first order reaction, you will able to find out the value. Then question number 7, it is also numerical. The equation, the equilibrium monomer concentration Me for radical polymerization 1,3-butadiene at 77 degrees centigrade is, okay, these values are given delta S, delta H, and we need to find out a monomer Me. Okay, so monomer concentration at the equilibrium. Okay, so delta H given, delta S given. So we need to use this equation. Okay, I think it is taught in your lecture. Okay, so if you put this value here, you will able to delta H value is given, delta S is given, R is rate constant, and Tc is temperature. Okay, so temperature, how much it is given? It is 77. Okay, so 273 plus 77, like that. If you add, you will able to find 350. Okay, because it is we need to put value in Kelvin. It is centigrade. Okay, so okay, it will be 350. So temperature is given, then you need to find out gas constant is, you already know. Okay, so you will able to, if you solve this, you will able to find the value of this concentration. Okay, question number 8. Question number 8 is a chain polymerization of styrene can be associated with the thermodynamic parameter is. Okay, so see, chain polymerization of styrene Okay, uh, so styrene will be what we can say, it will be autopolymerized, okay, or spontaneous. The reaction will be spontaneous. So why if any reaction is spontaneous, then it gives free energy. Change in gives free energy will be negative. We know about that. Okay, it is rule. If any reaction is spontaneous, then gives energy change is negative. Okay. So how we will solve here? So delta G is equal to delta H minus T delta S. So we finally need this value negative. Okay. Then only our reaction will be spontaneous. Okay. So now you can find out the value. So delta H, it should be negative. It should be, this value should be negative, na, delta H. Then minus T delta S. So this value should be positive. T is constant. Okay. Don't worry about T. So delta S, because only delta S and delta S asked, huh? So we assuming that T is constant. So T write like that, and delta S should be positive. Okay, if it will be negative, then negative will be positive, convert in positive. Okay, so overall it will be positive, and might be this reaction will be not spontaneous. Okay, so it is condition here that the delta S should be positive. Okay, so that's why, sorry, just a minute, delta H will be negative and delta S also will be negative. No, it not will be positive, because when polymerization is there, okay, because monomer are converting in polymer, so disturbance is decreasing, so it will be also negative. Okay, so this concept will not work here. It will be also negative. Okay, and negative, it will be positive, suppose. Okay, then also delta H, delta H should be more negative. Okay, so overall value should be negative. Like that it will be there. Okay, because entropy will not decrease here. Entropy will not increase here. Entropy will be decrease, because monomer have very means you can say more degree of freedom compared to polymer. Polymer chain has less degree of freedom, so delta S will be negative. Okay, so delta S will be negative. Delta H, obviously it will be negative. Okay, so A is right answer. Okay. Now, okay, so it is given here. Delta is will be negative, delta is. Okay, so the reaction is highly exothermic. Okay, highly exothermic means it will release the heat. Okay, so whenever a reaction release the heat, it delta H will be decreased. Okay, and it will be less than zero. Okay. Uh, for the exothermic convection, because pi bond in styrene of styrene monomer molecule convert in sigma bond. So sigma bond is more stable and less energy. Okay, whenever anything is stable, then it has less energy. Okay, so sigma bond is strong and stable, so it has less energy. So when pi bond convert to sigma bond, it will lose energy. So it enthalpy will be decreased. Okay, so it is about all about enthalpy. Then the negative delta S for polymerization arises from the decrease of degree of freedom or randomness. Okay, because polymer, if you see the polymer, there are many molecules of polymer, small monomers, you can say small monomers, which can randomly wander here and there. Okay, so their degree of freedom are very high compared to polymer, because after making after when monomer make polymer chain, their degree of freedom is decreased. So that's why rate of disturbance also decrease, or finally you can say the delta S will be decreased, entropy will be decreased. Okay, so delta S will be negative for this question. Okay. Now question number 9. MMA, it is I think methyl methacrylate is polymerized by thermally initiated free radical. Okay, it is thermally initiated free radical mechanism at 70 degree. The initial monomer and initiator concentration is 1 m and zero point 0. Okay, we know that initiator concentration is very low. See, it is under around 1000 times lower. Okay, and at the polymerization temperature of 70 degrees centigrade, the initiator efficiency is zero point 0.6. Okay, so initiator efficiency is generally denoted by F. Okay, the rate constant at the polymerization temperature are given below. Kd is given. Okay, Kp is given, and Kt is given. Okay, so all these rate constant are given, and the question is asking if the value of steady state free radical concentration after 1 hour from the reaction is x. Okay, so we need to find out that what will be the concentration of the radical free radical concentration. Okay, free radical concentration we need to find, and after 1 hour. Okay, so we need to find out this value. So we know that at steady state free radical concentration is given by following equation. Okay, so this is the monomer concentration after 1 hour. Okay, so if you put value in this equation, you will get the answer. Okay, AF is given, conversion, it is around 0.60. Okay, KD is given, KT is given, I0 is given 0.001. Okay, and E minus KT, KD and T is also given. Okay, time. Okay, so it is also given. If you put this value here, you will able to solve the answer. Okay, so now finally last question, question number 10. So it is also numerical question. Consider a thermally initiated radical polymerization with no chain transfer. Okay, we are assuming that there is no chain transfer and termination only via bimolecular radical between propagating radicals. Okay, so chain transfer is not there, but and it is terminated only via bimolecular reaction between the propagating radical. At the end of the reaction, the polymer produce the average number of initiator fragment per molecules is 1.45. See, if this polymer contain two initiator, okay, so we can say this polymer is made by coupling. Okay, but it is not made by coupling because the ratio is less, so the value is less than 2. Okay, 1.45 only. So we can say that there is some coupling reaction Kc, and there is some other transfer reaction also. Okay, so by this two mechanism, you can say uh, mis termination is going on by okay. So we need to find out what are the ratio of coupling and what are the ratio of transfer. Okay, it is 1.45, so it is not purely transfer only. Oh, sorry, coupling only. Okay, so by this value already given. Okay, sorry, B. What is B? Let me solve step by step. Okay, so termination by coupling result in two initiator fragment per polymer. Okay, I already explained. If termination is caused by coupling only, there should be two initiator fragment, while disproportion result in one initiator fragment per molecule. If transfer is there, okay, means suppose it is initiator, I can say A. Okay, if it is like that, and if it is reacting with another monomer or another chain, okay, so it is transferring something. Okay, so you can say A M initially, suppose it is like that, it is transferring one reaction. Okay, and then it is making radical. Okay, so now it is dead chain. Okay, now it is dead chain, but it contain only one initiator. Okay, so if it is if ratio is one, if the value is 1, you can say it is totally chain transfer reaction. If ratio is 2, then it is totally coupling reaction. But it is not this case. It is in between 2. Okay. So the value is more than 1 but less than 2. Okay. So we can say that there is some coupling as well as some transfer reaction is there. Okay. So now we need to find out the value. So we can find out value by this equation. Okay. So fraction of propagation chain unit undergo termination by coupling is denoted by A. Okay. And fraction of propagation, okay, so it is fraction of coupling. Okay, so A, so total 1 minus A will be uh, propagation chain undergo termination reaction. Okay, we are assuming that total termination is 1. Out of that, A is due to coupling. So obviously 1 minus A will be due to termination. Okay, so by this way you can find out this value. Okay, so B, so the average number of initiator fragment per molecule B is given by this equation, 2 divided by 2 minus A. Now uh, if you modify this equation, you will able to find, okay, this equation B 2B minus BA equal to 2, or we can take common B. Okay, it will be 2 minus A equal to 2. Then if B will be shifted here, yeah, right hand side, then equation will be 2 minus A equal to 2 upon B. Okay, finally you can remove this bracket. Sorry. So it will be 2 minus A. Okay, now uh, you can shift it like we need to find out this one. Just a minute. So it will be just let me write it. B is equal to 2 minus A. So what we did, 2B minus BA equal to 2. Then we took B common. So 2 minus A. Then 2 upon B is equal to 2A. Okay. Then we can say 2 minus 2 upon B equal to A. Okay. Or we can take B common. So it will be 2B minus 2 equal to A. So this is the final equation. Okay, so this is the final equation which is written here. Okay, by putting the value, B is given already. Okay, 1.41. So sorry, B is not given. What value is given? Uh, yes, B is given, 1.45. Yes, 1.45 fraction of what is B? B is fraction of propagation chain undergo termination by disproportion 1 minus A. Okay, and the average number of initiator fragment per molecule. Okay, so average of initiator fragment per molecule B value is given 1.45. Okay, so if you put the value 1.5 here, you will able to find out A. So A will be 0.62. Okay, 62%. Just a minute. Hello. हाँ हाँ क्या क्या हुआ 8 बजे आऊंगा Okay, learners, I have solved all these 10 questions. Okay, I have already solved. So now I am giving you 5 minutes, and I will also take rest for 2 to 3 minutes. Then I will start. Okay, and I will discuss some important concepts of week 4. Okay, so we will start after 3 minutes, 2 to 3 minutes. Okay.
Okay, sir.
Yeah. Okay, now we will discuss about the week four concepts which were taught in last week. Okay, so polymerization process. There are two type of polymerization process: heterogeneous and homogeneous. Okay, I think you know about this term very well. Okay, homogeneous and multi-phase or heterogeneous. Okay, so homophase means if any system contain only single phase. Okay, like still water. Okay, so if it is pure water, then it is contain only a single phase. If you add alcohol in water, then also it will be dissolved. Okay, so you will able to find only homophase, but somewhere you will able to find heterogeneous phase. Okay, suppose you are adding sand in water, okay, or dust in water or something like that, so you will able to find heterogeneous phase. Okay, so we will discuss that how polymerization can be done by homogeneous and heterogeneous phase. So some homogeneous system may become heterogeneous. Okay, homogeneous means suppose first of all suppose you are adding some monomer and there is some solvent. Okay, so monomer dissolved in solvent. Suppose you are adding some initiator which is also dissolved. Okay, and it is making a one homogeneous solution. Okay, but when it will polymerize, it will make different chain. Okay, it will make chain, polymer chain, but these polymer chains are not able to dissolve in this solvent, whatever solvent you are using. So it will be precipitate, or it will be suspended or precipitate, whatever. Okay, but now this system is not homogeneous. Now it is heterogeneous. So this is only explaining here that some homogeneous system may become heterogeneous as polymerization proceed as a result of insolubility of polymer. Okay, so resulting polymer is insoluble in your reaction media, whatever solvent you are using. Okay, either water or organic solvent, whatever you are using, it is not soluble in this film. Okay, so this classification is usually based on whether the initial mixture is homogeneous and heterogeneous. So okay, so it will be confused. Okay, so let me somebody in waiting room. Okay, so it will be confused, okay, because as we discussed here that this system was initially homogeneous, but when polymerization happened, it become heterogeneous. Okay, so that's why we put one clause here that this will be classified on the initial reaction mixture. Okay, it will be classified on initial reaction mixture. If initial reaction mixture is heterogeneous or homogeneous, whatever is there, we will classify according to that. Okay, so it is a homogeneous and heterogeneous. Then polymerization process. Okay, so what are the homogeneous type of polymerization? So we already discussed about homogeneous. So first of all, it is melt polymerization. Melt polymerization means you are melting your reaction media. Okay, so it should be at high temperature, or you can say temperature should be higher than its melting temperature, or is glass transition temperature Tg, Tm or Tg. Okay, so the reaction temperature should be higher than Tm or Tg. Then only it will be melt polymerization. Okay, some examples are given here. And solution polymerization. Okay, in solution means suppose you have one organic solvent and you are putting your monomer and initiator whatever inside this organic solvent, and now it is soluble. So you will able to find only one phase. Then polymerization will be there. It will the polymer is also soluble in that case. Okay, so overall the composition is homogeneous. Okay, so there are some example solution of polyethylene like that. Now we discuss about the multi-phase heterogeneous. So obviously this name says there are two or more phase emulsion. Okay, so emulsion means it is making a, solution of two liquid which are not miscible or okay. So this type of solution will be formed. So it is emulsion polymerization, and sometimes suspension also. So it is making some solid particle in the media. Okay, so this type of polymerization also will be discussed. It is already discussed, but I just explain some. I will just repeat it. Okay, and then just heterogeneous, multiphase. You can say in emulsion and suspension they are multiphase. Okay, in heterogeneous precipitation polymerization we already explained. If some polymerase is precipitate, initially it was homogeneous, then it will be precipitate. Okay, then polymerization with a heterogeneous catalyst. Okay, if your catalyst is heterogeneous, then also phase will become heterogeneous. So you can say it will be also heterogeneous polymerization. Then interface polymerization. Okay, so it will be also uh, heterogeneous because interfacial polymerization, what will happen, suppose this is the it will be happen at interface. Okay, so suppose it is A, it is B, these are the two solvent A or B. Okay, and at the interface suppose some polymerization is there. Okay, so it is also heterogeneous polymerization because there are two different phases are there. And then solid state polymerization, so it will be occur in solid state. uh, there means two or more solid states are there. Okay, so it is also making heterogeneous. Then in homogeneous sorry, in homogeneous polymerization, melt polymerization, okay, I have already explained this thing, that the monomer as well as the resulting polymer are in the melt state. Okay, it should be above Tg or Tm. Okay, and in solution polymerization, the monomer and resulting polymer are in solution under the condition of polymerization. Okay, so they are making means solution, they are making solution, and the solution is homogeneous. Okay. Multiphase polymerization or suspension polymerization, okay, also called pearl or bead polymerization. It used to produce small spherical beads. It can be employed with water insoluble monomer and initiator. Okay, so suspension will be generated in water insoluble monomer. Okay, so a suspending agent is added to okay, so if you are adding anything which is water insoluble, okay, if you are adding anything which is water insoluble, then how this phase will be remain uniformly distributed in the water. Okay, so you need to add some suspending agent. Okay, some suspending agent which will able to stabilize the suspension of the monomer in water. Sorry, in the form of droplet, because otherwise it is insoluble. Sorry. So if you add this suspension, then only it will be make uh, if you add suspending agent, then only the suspension will be created, and this monomer and ester will be able to make suspension. So examples are given here. Then precipitation polymerization. Okay, so name says the monomer are insoluble. The monomer are insoluble, but the resulting polymer precipitate out. Okay, so initially your mixture is homogeneous, okay, or solution, but after that it will make polymer precipitate. So it will become in heterogeneous phase or multi-phase, you can say. Okay. These are the another example of multiphase polymerization. Polymer with heterogeneous catalyst. Polymerization where the catalyst which is insoluble in either the monomer or the solvent used for polymerization. Okay. Heterogeneous catalyst, obviously it is saying that the catalyst is heterogeneous. Okay. Otherwise all things are you can say one phase, and if catalyst which is heterogeneous, then also this polymerization where the catalyst which is insoluble in either the monomer or in the solvent used for polymerization. Okay. So either see either in or. Okay. So catalyst should be soluble in one case, in one phase, and insoluble in another. Means it should be, if it is if it is soluble in monomer, then it should be insoluble in another insoluble in either in the monomer or the solvent. Okay, so it should be at least insoluble in one phase, either in monomer or solvent. Okay, then only it will make multiphase. Then emulsion polymerization. So emulsion polymerization are essentially carried out in water medium. Okay, so emulsion, so we are making emulsion, okay, in water. So of three component, so monomer, initiator, and surfactant. These are the three entities which are making uh, emulsion in water. Only the initiator is soluble in water. Okay, see, initiator is soluble in water, while the monomer and the polymer are insoluble in water and are dispersed as very small spherical particle. Okay, so monomer, initiator, and surfactant, they are making some relationship, you can say. Okay, that's why they are insoluble in water. Okay, monomer, initiator, and surfactant, only the initiator is soluble in water, while the monomer and polymer are insoluble in water. Okay, and are dispersed as well. Okay, so it will be dispersed, so you need to use some surfactant. Okay, so surfactant is already given here. Okay, and we will discuss example, so it will be clear from by explaining example. Okay, then heterogeneous polymerization. So interfacial polymerization I have already explained you. Low temperature polymerization technique for synthetic step growth polymerization. Okay, it is done by step growth polymerization. Polymerization of two reactant is carried out at the interface between two liquid phases. Okay, so two liquid phases are there, like there. Okay, these are the two liquid, is you can say A and B. Okay, so polymerization in the two reactant is carried out at the interface between two liquid. Okay, so liquid A contains some type of reactant, it contains some type of reactant, and when uh, they are mixed, when they are mixed, then polymerization occur at the interface. Okay, so at the interface the polymerization will be occur. Okay, then solid state polymerization. So what is solid state polymerization? It is also part of heterogeneous polymerization. It is also type of heterogeneous polymerization. So we can say process wherein the chain growth reaction occur predominantly. Okay, chain growth reaction occur predominantly in the solid state and the amorphous region of polymer, and the reactive end group are concentrated in amorphous region and excluded from the crystallite. Okay, so in solid state, it is polymer is already solid state, where reaction occur predominantly in the solid state and amorphous region. Okay, amorphous region of polymer, where the reaction will be occur, and the reactive end groups are concentrated in amorphous region and excluded from the crystallite. Okay, so uh, it will form polymerization will be there in amorphous region of polymer, and then it will be excluded from the crystallite. Okay, then these are the free radical polymerization process. Okay, so these are the free radical progress process which only monomer. Okay, with only monomer. So there is nothing, only we are using monomer, and uh, it is done by free radical process, but we are using only monomer. Okay, so reaction will be occur in monomer, and it will no solvent is used. Okay, not solvent being used, only monomers are reacting, and it will make bulk polymerization. Okay, see, only because we are using only monomer, so reaction rate will be very fast. Okay, and it is called as a bulk polymerization. Then in a solvent, so you are using solvent, so it is very good if you are using solvent. The reaction rate will be slow, but it will you will able to you will able to heat transfer, because when polymerization will be occur, excessive heat will be generated. So you will be able to transfer this heat by using solvent, and then you can also control the viscosity. Okay, otherwise the viscosity in you can say bulk polymerization viscosity will be increased drastically, and it will be very tactic for stirring and further polymerization. But in solvent, these facilities are there. Then with monomer disperse in aqueous phase. Okay, so see, if monomer, so you need to memorize this thing that if monomer disperse in aqueous phase, then it is called suspension polymerization. Okay, so monomer disperse in aqueous phase. Okay, in second case, when produced polymer are dispersed in organic solvent. Okay, so in first case monomer, but in second case we are discussing about the polymer, and it is dispersed in organic solvent. Okay, then it is called dispersive polymerization. Okay, so these are the little things which you need to memorize. And finally emulsion polymerization. Okay, so emulsion will be formed in water, and how it will be there we will discuss in upcoming slide. Okay, so bulk polymerization. Okay, now we will discuss little. Now we will discuss in little broad way, in detailed way. Okay, what are these polymerization are? So bulk polymerization simplest. It is the simplest polymerization. Only monomer and monomer soluble initiator. Okay, only monomer we are using. Okay, a monomer soluble initiator. Okay, so initiator is also soluble. So only single phase. Polymer are also soluble in monomer. Okay, so resulting polymer is also soluble in monomer. Okay, whatever monomer you are using in you can say liquid phase is monomer in liquid phase. So although it is generating polymer, then also polymer is also soluble in monomer. So it is not making different phase. And the mechanism which is applied here is free radical kinetics. Okay, then the advantage is monomer concentration here is high, so rate of polymerization will be very high, and molecular weight will be also high. Then it will because we are not using any solvent. Okay, so we can uh, we can reduce the problems which are created by impurities contained in solvent. Okay, because solvents contain some impurities which can be act as a chain transfer or chain stoppers, or okay, so some molecules are there in very low concentration, but they act as a retarding of polymerization, or you can say inhibition of the polymerization. Okay, so it will produce high purity minimum contamination product. Okay, and this type of is product are using for optical application. Okay, we know that in for optical application we need very good type of polymer. Okay, due to high visibility and all things, that's why we use this type of polymerization. Okay, there are some disadvantage also. We know that reaction rate is very fast. Okay, so whenever reaction rate is very fast, and it will make a high molecular weight polymer. So after some time you will able to find a viscous solution. Okay, so if a solution is viscous, then it is very hard to manage. It's very hard to handle. Okay, so processing will become very typical if the viscosity of your uh, reaction mixture is high. Okay, so this is the disadvantage. that viscosity become high even at low concentration. So stirring become difficult. You need to use high power stirrer, okay, because when polymerization is there, it is very viscous solution and also difficult to handle. Reaction rate is very high, so it will also produce abundance amount of heat which you need to maintain. RT decrease, okay, yet high conversion due to Thomas drop effect, okay, or you can say gel forming, okay, it will make gel, so it will the termination reaction will be very uh, decrease, okay. So due to this reaction mechanism of bulk polymerization, it will also form degradation, coloration, branching, and cross-linking, and high dispersity value. Dispersity value, if we know that if dispersity value is very high, then the importance of polymer will be decreased. Okay, so these are the disadvantages of bulk polymerization. So by making some you can say awareness or some precautions, we can skip this disadvantage little bit, which are keep to low conversion, separate and recycle the unreacted monomer, okay. So these are the some precautions we need to keep in mind while using this mechanism, okay. Then a solution polymerization, so it is already very well explained. So monomer, solvent, and soluble initiator. Okay, these all things are soluble. Free radical kinetics will be there, and produce polymer is also soluble. Okay, so it is solution polymerization. So advantage is there that here something is there which can manage this polymerization, or you can say some medium is there. Okay, which is called as solvent. So solvent act as a dilutant and aid in removal of heat of polymerization. Okay, so by using this solvent, we can remove this excess heat. Al- Also, the uh, viscosity will not increase as much as increase in bulk polymerization. Okay, so it will make easier to stir. Okay, then thermal control is easier than the bulk. Okay, thermal control means whatever which heat transfer and all, it will be also very easy. It will be also easy for the solvent solution polymerization compared to bulk polymerization. There are some disadvantages also for the solution polymerization. Okay, that concentration of monomer is lower. Okay, concentration of monomer is lower compared to bulk. Hence, rate of polymerization is slower, and similarly, molecular weight is also lower. Chain transfer to okay solvent. See now, solvent is providing media, but solvent contain also some impurities. These impurities can take part in chain transfer reaction. Okay, so if chain transfer reaction is there, then molecular weight will be lower. Okay, and after that, at the end of reaction, you need to remove the solvent also from the okay because you need only polymer, so you need to remove the solvent. These solvents are made organic compound, we already know, and these are very hazardous also. Okay, and we need to remove it. We need to do extra efforts, and it will also create environmental pollution and all. Okay, so these are the disadvantages of solution polymerization. Then heterogeneous polymerization. Okay, so in heterogeneous polymerization, monomer soluble initiator, okay, and water and disperse. Okay, so see water. If you are using water, this monomer and monomer soluble initiator. Okay, these will not soluble in water. Okay, so it will make some type of suspension. So you need to add some dispersant also, so which can stabilize this suspension. So similar to bulk polymerization in kinetics. Okay, so kinetics is same similar to bulk polymerization. So the process is initiator is dissolved in monomer and then preheated dispersing medium is added. Okay, so if you are first initiator is dissolved in monomer, so first task is completed. Then we need to use, then we need to add dispersive medium. Okay, like water. Okay, we need to add. Then vigorous stirring convert the monomer content initiator into small drop of size. Okay, after adding dispersive medium, you need to stirring vigorously so that uh, this insoluble monomer and initiator solution convert in suspension. Okay, then to keep this suspension stable, we need to add some dispersion pressure. Okay, the weight percent of dispersion is very low. Okay, but we need to add it. Otherwise, again, it will make it coagulation will be there. Something will be precipitated. Okay, and reaction will not uniform. So we need to add this dispersion percent. Okay. Okay, so what are the advantage of this suspension or heterogeneous polymerization is aqueous medium. Okay, we are using aqueous medium water. Okay, as a what say suspensing medium is aqueous water, so it will dilute. Okay, and add excess heat, similar to solvent. It will also use. It will also help to use. It will also help to reduce heat. High polymerization rate and high molecular weight also similar to bulk polymerization. Okay, then polymer produce as beads and can be taken out by filtration. Okay, so by this way you can remove by filtration. So here as we discussed in solvent polymerization, we need to remove solvent at the end of polymerization, but here it is also not need to worry. We just can filter it, separate it by filtration, and we need not to remove this solvent also. Okay, because it is water only. Okay, then disadvantage is polymerization need to be completed. Okay, then also you then only you can separate it, and dispersion may impart impurities. It is already, if impurities are there, then it will be hampered the polymerization process. Now we have discussed this thing, suspension. Okay, now we are discussing dispersion. So here monomer, soluble initiator, and organic solvent and dispersant. These are the four things which are taking part in this polymerization. Okay, organic solvent is there. Then monomer and soluble initiator. Okay, so organic soluble initiator. So polymer formed are insoluble in. Okay, so polymer will be insoluble. Okay, then polymer remain dispersed because of presence of dispersant. So why we are using dispersant? To disperse the polymer. Okay, polymer grow in size as the absorbed monomer get polymerized, and size of polymer produce around 1 to 10 micron. Okay, whatever these are things. So these are about dispersion polymer. What are the advantage and disadvantage of this polymer? Okay, now we are going to discuss about the emulsion polymerization. Okay, so mechanism of emulsion polymerization will be discussed. Okay, why we are discussing emulsing polymers in detail? Because it is industrial important polymerization. Okay, so many important polymerizations are produced by this polymerization process only. Okay, great industrial importance. And due in World War II, 1,3-butadiene by using 1,3-butadiene in styrene, synthetic rubber was produced. Okay, so that's why this process was became very popular. Okay, and this was the start of synthetic rubber in the United States. Okay, so now you can say that synthetic rubber is part of our life. Okay, but it was first produced in Second War. Presently, the predominant process for the commercial polymerization. Okay, commercial polymerization means it is beneficial. Okay, there are many process for polymerization, but it should be economically favorable. It should be environmental friendly. Okay, and it should be easy. So this all these all characteristics are contained by emulsion polymerization. Okay, so some examples are given here. I will not worry about that. Okay, so what is the importance of emulsion polymerization is it will make water product means okay latex is what the product a colloidally stable dispersion of particulate polymer in water. Okay, so it will making water emulsion, okay, which is called latex, which contain polymer. Okay, so that's why it is very ready to use and it is very popular. Okay, so product a colloidally stable dispersion. Okay, it is producing a stable dispersion of particular polymer in water known as latex and can be used directly in application like paints, coating, finished and floor. Okay, and the medium is water, so it is not as dangerous. It is not dangerous as solvent, organic solvent. Okay, it is water only. Okay, so it is also beneficial in the perspective of environmental friendliness. Okay, then size of particle are about 3 order of magnitude smaller than suspension polymerization. Okay, so it has small particles are there. Then similar advantage of suspension polymer. Okay, also it is emulsion, but it is similar advantage of suspension polymerization. But suspension polymerization are little it contain organic solvent role, but this is more favorable for uses. Mechanism and kinetics are different from normal radical chain polymerization. Okay, so its mechanism is different. So its mechanism only make this polymerization unique. Okay, the mechanism of emulsion polymerization making it unique. Okay, so a molecular weight can be increased without compressing polymerization rate. Okay, so it will be discussed when we will discuss about the mechanism, then this concept will be clear. Okay, so in emulsion polymerization, what are the ingredient and some given here is like water. Okay, water and monomer ratio. Monomer, water insoluble or slightly soluble. Okay, so monomer are there, and then initiator, it should be water soluble. Okay, initiator water soluble, and then emulsifier surfactant. Okay, it should be more than critical missile concentration. Okay, then only missiles will be formed. So we need to know that which surfactant we are using and what is its CMC. So its concentration should be more than CMC. Okay. So some anionic surfactants are given here. Okay, anionic means negative ion content. Salt of fatty acids. Okay, so it will be like that. Okay, so it's salts of fatty acids like that. Okay, or sulfates. Okay, sulfates also can be there. Okay, like that sulfates either oxygen will be also. So sulfates can also can be there. Okay, so these are the anionic surfactant which are used for emulsion polymerization. I will not discuss about that. It is already what are the ratios and conditions are given here. Okay. See now here from here we will discuss. Okay. So when we add surfactant, okay, initially they accommodate at the surface of medium. Okay, like that. But when we increase the concentration of this surfactant, they will form micelles. Okay, this spherical shape is represented because it is 2D shape, so it is looking like circle, but actually it is a spherical shape. So when it will form, when the concentration of surfactant is more than critical micelle concentration. Okay, if it is more, then only it will make micelles. So this is the thing which we require, okay, for polymerization. This is the, you can say, host which we require for surfactant. Okay, so by this curve you can understand then that in y-axis it is representing surface tension, okay, and in x-axis it is presenting concentration, low concentration of Cb, means surfactant concentration. So when you increase the concentration, the surface tension of the system will be decreased. Okay, why it is decreasing up to here only? Because when you where you are adding surfactant, the surfactant molecules are accommodating on the interface. Okay, so it is reducing surface tension. But when there are sufficient molecules which are already accommodate for reducing surface tension, then excess of this molecule will remain in the medium, and further if concentration will be increased, then they will form micelles. Okay, this micelles can be again converted in individual surfactant molecule, and this is the equilibrium. Okay, so it will make some micelles, and here, okay, so we are increasing concentration, so at that concentration this CMC will be formed. Okay, so we required concentration of surfactant very high than CMC. Okay, for the polymerization process using this uh, emulsion process. Okay. Also, if you are seeing this molecule, okay, this had two part. First one is hydrophobic, and another is hydrophilic. Okay, hydrophilic, I will write HP and N. Okay, so you can say it is a hydrophilic, so I am writing, sorry, hydrophobic, it is hydrophilic plus, and this is the minus. Okay, so means hydrophilic means it love hydrogen, it love water. Okay, hydro means water, it love water. So see, this is the water only, so medium is water, so this sphere will remain like that only. Okay, because it love water, but the tail of this molecule is love organic substance, and it has, it is threatened by water, you can say it has fear from the water, so it will be like that, it will try to escape from the water. Okay, so like, so that's why this type of orientation will be generated, and it will form micelles. So this is the reason why micelles is formed. Okay, why this surfactant molecule not remain individual, why it is converting there? So this is the reason, due to its bipolar nature, hydrophilicity and hydrophobicity, they are arranged in micelles. Okay, so these are the this slide representing the mechanism of emulsion polymerization. So here you can see some micelles are there. This M represent monomer, I represent initiator. This you can say rectangle, it is not a square, we can say rectangle, you can say it is water, this medium is water. Here a big droplet, this droplet, you can say it is a emulsion, and this droplet is water. Okay, this this is the water droplet. Okay, and monomer is soluble, so it will be found in this droplet. Okay, here also monomer will be there. Okay, no, sorry, initiator will be just because yes. Okay, so initiator which we used are soluble in water, so it will remain soluble in water, but monomers are generally insoluble or lightly soluble in water. Okay, so what these slides are showing, we just discuss the aqueous phase. Okay, so remaining this all is water, so it is aqueous phase. Okay, in water there are different type of initiator, monomer, micelles, and all these droplets are there. Large droplet, see 1 to 100 micron, so large droplet of monomer maintained in suspension by absorbed absorbed surfactant molecule and agitation. Okay, so when you add water in your medium and if you agitate it, it will make suspension and it will make suspension of large bigger droplets. Okay, so uh, around what this saying, large droplet of monomer. Okay, so this droplet containing monomer. Okay, so large droplet of monomer maintaining in suspension by absorbed surfactant molecule. Okay, so surfactant molecules are there, you can see. Okay, and then small monomers swollen micelles. Okay, so you can see here some monomers are there inside this because monomers are also organic compounds, so they will try to move inside. Okay, where hydrophobic part of surfactant is there. Okay, and here it will start polymerization. So small monomer swollen micelles. Why it will be swollen? Because this monomer will be react and make polymer. So it will occupy some space. So that's why this micelle will be swollen. Okay. So small monomer swollen micelles which are far greater in number than droplet monomer droplet but contain a relatively small amount of total monomer. Okay, so what this sentence is saying, that small monomer solar miscible which are far greater in number. Okay, so number of these micelles, swollen micelles, are far greater in number than monomer droplet. Okay, these are the monomer droplets but contain a relatively small amount of total monomer. Okay, so monomers are, the number of monomers are small in these micelles, smaller micelles, but the number of monomers is small, but the number of micelles are very high. Okay, so you can say micelles are 10 to the power 19 to 10 to the power 21, but here it is 10 to the power 12 to 10 to the power 14. Okay, so you can see difference. So the number of, so concentration of micelles is very high compared to monomer droplets. Then total surface area of the micelles more than two order of magnitude to total surface area of monomer droplets. Okay, so if you compare the area of droplets, I can write D, and area of micelles, so it is bigger. And how much it is bigger? It is two times bigger. Okay, so two order of magnitude of total surface area. So total surface area of micelles more than two order of magnitude of total surface area. Okay. Now we will discuss little bit about. Okay, so it is the mechanism of this emulsion polymerization is uh, explained in interval 1, interval 2, 3, like that. Okay, so we will discuss what is the okay, what is happening initially. It is called as a interval 1. So oligomeric radical species. Okay, oligomeric means we know when some monomer react, it will form oligomeric radical species. So in interval 1, this type of phenomena can be happen. Termination in the aqueous phase to produce uh, termination in the aqueous phase to produce species that are surfactant like. Okay, small with what is the surfactant? It is a hydrophobic part means small. You can say it is small polymer. Okay, so in interval 1, it can be generated. Okay, by termination. By termination, small type of oligomer can be generated which will be look like surfactant molecule. Okay, so termination in aqueous phase to produce species that are surfactant like, then continue to propagate until there is the critical site at which they become surface active. Okay, so another case is it will be polymerization will be continue. Okay, so it will be propagate until it will reach critical size and become surface active. Okay, and grow still further and reach another critical size as they become insoluble. Okay, initially it is soluble, but at insoluble, or and when it will be insoluble in the aqueous phase, it will be precipitated from the phase. Okay, so these are the phenomena is happening in interval 1. So no polymerization in monomer droplet. Okay, so what are we are discussing the monomer droplet, bigger one, which contain monomer inside, and here it is contain uh, like that. Okay, so this monomer, so polymerization will not occur in this droplet. Okay, so it is already saying, it is only saying this thing, no polymerization in monomer droplet. And the system consists of three type of particle. Now in interval 1, system consists of three type of particles. Monomer droplets, we already explained, monomer droplets is there. Inactive micelles. Okay, so see, in some micelles monomers approached and they start polymerization, but there will be some inactive micelles also where no monomer particle, they are micelles. Okay, due to concentration of surfactant they made micelles, but polymerization not started yet. Okay, then active micelles or polymer particle. Okay, so where polymerization is going on. Okay, so these are the phenomena in interval 1. Okay, so interval 1 is generally occur from 0 to 10 to 15 conversion. Okay, so when reaction occur up to 10 to 15%. Okay, so see now some data are given here. Monomer in micelles. Okay, monomer in droplets. Okay, monomer will be remain in micelles also, which are getting polymerized. Monomer will be remain in droplets also. Okay, because these are not polymerized, so it will be remain same. And monomer in polymer particles also. Okay, because some polymerization is oligomers are generated, so some monomer particles are in polymer. So you can say that monomer particles are distributed in micelles, droplet, and polymer particles. Growing number of particle, and similarly growing number of polymer particles. Okay, so some particles are growing, some polymer particles are terminated and making similar structure of surfactant. Okay, so where also polymer, we can say that we are already discussing that where the monomer has consumed in interval 1. So it is micelle, droplet, polymer, and polymer particles. Now what will happen in interval second? Okay, so when concentration mp of monomer within particle remain constant. Okay, here the concentration of monomer in particle remain constant. Okay, so this is the, suppose this is the micelles, and inside this micelles some particles, some monomers are there. Okay, and when they are when they are reacting, they are making some polymer. Okay, again red, not red, suppose yellow. Okay, so are making some polymer. So what will happen, the concentration of monomer will be decreased, so it will be fulfilled by outside monomer concentration. Okay, So concentration of monomer within the particle remain constant. Inside this particle remain constant means polymerization is going on inside this micelle. Okay, but it will be constant because monomer is being supplied from the outside. The number NP particle per unit volume of latex remains same. Okay, so number of particle per unit volume. Okay, so the micelles, now disactive micelles are destroyed. Now only active micelles are there, and in active micelles polymerization is going on. So you can say that number of NP will remain constant and rate of reactions is also constant because now NP is fixed, means number of micelles is fixed, and reaction polymerization is fixed. Okay, so rate of reaction is also fixed. Since NP is constant, the rate of polymerization is also constant. This produce the polymerization in the interval second. Therefore, in interval third, MP and the rate of polymerization decrease continuously as the remaining monomer present in the particle is polymerized. Okay, after some time, the monomer will not be there. Okay, all monomer will be consumed. That at the end of the process, the monomer which remain in micelles will be also polymerized, but it will be not supplied from the outside. So you can say that at interval third, the polymerization rate will be decreased because monomer is not there. Okay, so concentration of monomer is decreased, and now it is not supplied from the outside. So the rate of reaction is decreased. Okay, and it is called as interval third. So here you can see here to here rate increase. Here rate of reaction is constant, and again rate of reaction is decrease like that. Okay, you can say this curve is you can say conversion with time. Okay, okay. So I am stopping here only. Yes, let me complete this slide. Then I have to stop because it is already 2 hours are completed. So interval second and third, we have already discussed that in interval second, interval first was from 0 to 15%, 15 or 10 to 15%. Now interval second, which is 15 to 16%. So no micelle surfactant, okay, no micellar surfactant, monomer in droplets, okay, monomer in polymer particles, obviously, and constant number of particles. Okay, because no missile surfactant are there because they are already destroyed, which are non-active missiles are already active. Uh, Non-active missiles are already destroyed. Now monomer in droplets, which are active missiles, okay, sorry, monomer in missiles, monomer in droplets, which is yeah, droplets, okay, due to emulsion, uh, or monomer in polymer particle and constant number of particles. And interval third, now all monomers are consumed, so no monomer droplets, okay, because already all monomer are already consumed. Monomer in polymer particles and constant number of particles. Particle will remain constant only, but it is, you can say, end of the polymerization. All monomer are consumed. Okay. So these are the end of this class. Okay. If you have any question, you can write me. I have already shared my email ID. Okay. So please write me. Okay. So I will able to answer. Okay. So thank you for being here. We will meet next week, Saturday, same time. Till then, bye bye.